And we're live. Go ahead.
All right, good morning, guys. So if you don't know me, my name is Michael Koontz. I'm a new PhD ecology student with Andrew Latimer and Malcolm North. And I study spatial structure of forests and how that might affect different colonization processes after disturbance like wildfire or drought mortality, pest outbreaks, that sort of thing. So today we're going to talk about plotting in R, just using base graphics. And so I just mean using only native functions, no extra packages to install or that. And there's really two, I guess, motivations for this particular presentation. So the first is that, as most of you know, R is super powerful and can create really amazing graphics, and it's where we do a lot of our stats, so it's nice to sort of keep all of those methods consolidated. But it's also pretty daunting to kind of approach this and try to learn how to make these plots. It's not an easy language to learn, and especially if you're coming from no programming background, that makes it pretty hard. So the motivation here is to sort of make it more approachable and to encourage you to start tinkering with it and get you started working with your own data and that sort of thing too. And then the second motivation is that I read somewhere that to be good at plotting in R, you should know or at least two, I guess, of the major graphics engines, so ggplot or lattice or base R. And I think the spirit of that message is right, that the more methods that you have at your disposal, the better you're able to tell your particular data visualization story, right? So I'm hoping to give you another tool in your toolbox for visualizing your data and telling your story that you want to tell. And that sort of also brings me to my disclaimer for this particular talk, which is that I make no claims about the superiority of any particular plotting aesthetic. My bias is that I use base R and I like the way that it looks, but there's no shame in plotting in ggplot or base R or Microsoft Excel. All data visualization is cool, right? So we're just trying to give you another tool in your bag to work with. Okay, so let's get started then. Was everybody able to get the script that wanted to? And sort of the format of this is we're gonna walk through it line by line together, and it's supposed to be interactive. And you can see from this script file, it's really big. And I sort of went back and forth of, like, should I just make a script file that's just enough to get through the hour, or should I put everything that I wish that I knew starting? And clearly I went for the latter. So we're not gonna get through all of it. So please feel free to stop me and ask me questions about whatever particular lines I'm running or why I ran something a certain way. And that's all good. So I'm sure somebody else would have the same question if you have it too, and that's all part of the interaction. Okay, so this is our script file here, and you can see I've got a ton of sort of metadata and comments up at the top. The comments are littered throughout the code too, so hopefully it's standalone. So once you go home and you're looking at it, the hope is that you can run it on your own too. And it makes sense, but my email's there too, so feel free to email me with any questions in particular about the script. And it's broken into two main sections, so the sort of basic methods for plotting, that's what we'll start with, and then sort of the intermediate few tricks that I find myself using most frequently to make my plots for presentations or for papers and that sort of thing. So any questions, I guess, before we get started? Okay, so we're going to start with the trees data set, which is, I think, really tractable. It's pretty small, and it's built into R, so you should be able to just run this trees line and see the entire data frame over in the console. And this describes the girth, the height, and the volume of 31 black cherry trees from who knows where. So this is the entire data frame, and running the dim function on it gives us the dimensions. So we have 31 rows and 3 different columns. This one happens to be small, but usually I would run the head of the function to just see the first 6 rows. And I guess before I go any further, is this big enough for everybody to see in the back? Good, okay. And so remember how we access the columns of data frame. We use the object name trees and then the $ operator and then the column name itself. So trees $ girth gives us this vector representing the entire girth column, and trees $ volume, running that line, gives us a vector representing the entire volume column in that trees object. And this base plotting function just takes in an X vector and a Y vector. So if we're thinking about our original data frame, girth, height, and volume, this girth, we're going to make our X vector, and the volume, we're going to make our Y vector. And those are our XY pairs going down for each record. So each row in that data frame represents a single record, and the XY vector, those rows match up for those records also. So just a very simple basic plot here. Oh, that's really small. Wow. All right, we'll make this a little bit bigger. So this is just the basic plot, right? And hopefully you guys are all also running this on your screen too, right? But so we've got the, what do we say? We've got the girth on the x-axis and the volume on the y-axis, and these are open circles that you can see very clearly on your screen. And then by using this type equals argument, we can change the plot to a line plot. And type B is a both lines and points. So again, just really basic, starting the plot and R kind of manipulations. This PCH argument here, I like PCH equals 19. That's the plotting character. So the open circles are one kind of plotting character. That's the default. The PCH 19, that's a closed in circle. And then the main equals argument adds a title to our plot. So here I just have girth versus volume for black cherry trees. And going further, we can add an X label. So right now the default is the actual, the column, like that whole name of the object that you passed into the X vector, the tree's $ girth. So we can change that using this xlab equals tree girth here, pass it that string. And ylab similarly adds a y-axis label. This LAS equals argument rotates the y-axis labels, like the actual labels on the tick marks, not the label itself, but the tick marks, so that they are within the reading direction, which is always nice for presentations and papers and that sort of thing. And then the color col equals, this will change the color of the plotting character of the points to the lines. So col equals blue, and now those points are blue. And bear with me here for a second. So when we start thinking about plotting different groups onto the same plot or using different colors within the same plot, we want to think about passing vectors to these arguments. And so we can create a vector using this C, lowercase c function, to concatenate. And that just takes several different elements and puts it into the same object, into a vector object. And so if we just highlight this internal part here, C, black, blue, we can see on the console that the resulting object is a 2-element character vector, black in the first element and blue in the second. And so if we pass that vector to our color argument, now we have 2 different colors within our plot, right? So the first point is going to be black, second point is going to be blue, third point is black, and it's going to recycle that vector down through the whole data frame. And we can do the same with the plotting character also. So here I'm passing an open circle, a C with a 1 and a 19. If we just run that part, now we have a 2-element numeric vector, 1 in the first element, 19 in the second. And again, now we see that the plotting character rotates, or it gets recycled through also. So hopefully you're thinking, why would we do that, right? Where we would just have the same vector recycle through over and over again. Which is good, right? We don't necessarily want to do that. We want to have a more meaningful way to tell which characters or which colors we want in the plot.
Would this be useful maybe if you have your data set up where it's like paired?
Yeah,
something like
totally.
One after the other.
Right. Yeah, I mean, if you know the structure of your data and you know that it happens to go one after the other, then by all means, it's pretty easy to just put in that 2-element vector, right? Yeah, and so the key there of knowing that it just recycles that same vector over and over again. So to look at plotting by group, we're going to switch data data sets to this iris data set, and then we're going to stick with iris for the rest of the presentation and for the rest of the script. So we'll really get to know it. We won't have to introduce any new data sets for the rest of the time. So we'll start just by looking at the whole thing, and this is possible again because this is a fairly small data set. It's just 150 records, and we have the measurements on different iris flowers. So just looking at the head of it. So we've got sepal length, sepal width, petal length, and petal width, and then a species, one of 3 different species in this data set. The dimensions tell us that we have 150 records and 5 different columns. And then running this structure str function on iris gives us some more information too about how it's sort of organized, the structure of that particular object. So let's expand this idea of passing the vector of colors to our plot function call. And we're going to cheat first by looking at what we want the finished product to look like, and then we'll work backwards and figure out how to make R do that automatically. So I'm going to start by defining a vector of the plotting colors that I want. So I know that there's 3 different species, and I'm going to plot this particular object using different colors for different species. And so looking at that particular object, we see this 3-element character vector, violet in the first element, purple in the second, and blue in the third element. And then here's the cheating bit. So I just looked at this data frame and I saw that there's 50 records for each of those species, right? So there's 50, starting at the top, 50 setosa, 50 versicolor, and then 50 virginica. So just to get us started, I'm using this repeat function, the REP. I'm passing it this plot.colors vector, which if we just run that part, remember again, that's just those 3 particular colors that we want to work with. And then I'm going to repeat each of those elements in that 3-element character vector 50 times. And call it a new object called color.vector. And running that, we see now we have 50 different violets, 50 different purples, and then 50 different blues. So now in our plot call, we're going to be plotting the petal length versus the sepal length as our X and our Y vector. I'm going to use those closed characters, plotting character equals 19, and the color is just going to be that color vector. So every single XY pair is going to have a matching color. And you know what? Just to make this, we're going to jump ahead. I'm going to use this character expander argument. So maybe we can start seeing these on the screen. But that comes later too. So CEX, the character expander, will make your plotting characters larger. So I'll add those in as we go also. And so importantly, notice that the length of these 3 different vectors are all the same. So calling the length argument on the petal length, on the sepal length, both within the iris data set, and then the length of that color vector that we created, they're all 150 elements long. So when you're sort of thinking about this, plotting your own data, imagine how it would look with all of those the exact same length. So every XY pair has its own matching color. And so to automate this process, we can take advantage of the fact that species is a factor. So remember, here's our entire data frame, just calling the species column with the iris $ species. We see that not only does R know that each of these elements is virginica, setosa, or versicolor, but it also has information about which of these 3 levels it represents, and that's just a feature of this particular mode being a factor. So we can also see that by running this as.numeric line. So R also sees, in addition to setosa, versicolor, and virginica, it also sees that, oh, the first 50 elements are the first level, the second 50 elements are the second level, and the third 50 elements are the third level. So I've just copied this next code, the plot colors from above, in case you hadn't run it yet. And now to create our color vector, we're going to take advantage of, like I said, knowing that species is a factor, and we're going to use this bracket notation, which lets you access different elements within a vector. And so the vector that we want to access elements of is plot colors, right? Which is just those 3 different plot colors that we want, one for each of those different colors. And now remember that R sees, when we run this iris $ species line, in that column it knows that there's 3 different levels, and it knows which of those levels it is. So essentially, we're going to see R is going to ask when I run this next line right here, we're going to access the elements of the plot.colors vector. We're going to access the first element for the first 50 times, the second element of this vector for the second 50 times, and the third element for the third 50 times. And just so that we can see this, I'm destroying the plot here, device off. So now there's no plot there. We create this color.vector and see what it looks like. And now, again, it's sort of replaced those different species with the different colors that we want to insert in our plot into our vector. So now plotting that line, I'm going to add the inner also.
If plot colors wasn't the same length as the factor levels of species, would it have been an error message?
If plot colors were, yeah, I assume so. What happens then? Well, no error, but I guess it would be.
It only matches the first three.
Yeah, I guess it would just match the first three. But yeah, I wonder what happens if we get rid of them. That might give an error, right?
That'll recycle it.
Oh, that'll recycle it too. Now we've got NAs when I tried to access the third element. Good question. So yeah, so now it's not plotting those NAs at the top. Yeah. So let's put it back to how we had it. Okay, so adding a legend. We can add a legend to a plot using the legend function, which just adds a legend to an existing plot. So this is one of those kinds of functions that rather than destroy the plot and create something new, it's just adding another feature to an existing plot. And the arguments that it takes, the first one is going to be the location where you want the legend, which you can specify as a character vector, top left, top right, top left or right, bottom left, bottom right also. You can also give it an exact XY coordinate too if you want it out someplace in the middle of your plotting space. I think that's also how you would do it if you wanted the legend outside of the space with a few other modifications too. So in creating the legend, we sort of build this up from the ground up, right? So we tell it exactly what we want to go in the legend. So here I'm saying, well, the plotting characters were 19, were those filled in circles. The colors, we only need that original character vector, those three colors that we're putting in. And then the legend equals arguments is like the actual text that you put onto the legend. And here I'm using the unique function to look at all of the iris species column and ask what are the unique elements in it. So just running that particular line, we see that R knows that just Justosa, Versicolor, and Virginic are the only three unique elements within that vector. That's going to be small too. Better. Okay. So yeah, so I just made the character expander to make our legend bigger. Hopefully you won't need to do that though on your machine. So we can start to customize that legend. So here I'm just recreating the plot to start from scratch without the legend on it. And this time I'm going to pass a character vector to the legend equals argument, because say I want to put the I to represent iris as the genus for each of these. And then I'm also using this bty equals lowercase n, which suppresses that border box, but that's just a personal preference that I like the way that looks. So like that. And then we can also change the font and the font family and the style of the font using the text.font argument. So here's the plot. And this text.font is 3. That's going to tell me or tell R to make all of those italicized. like that. So you'll see too in this script file, there's a few scattered about places where it's like a self quiz, right? So it's asking you to do the same thing that we just did, but with a different data set. So hopefully that would be useful to you when you're going back and looking at this too. Any other questions so far? Good.
I got a question.
Yeah.
Sometimes when I've been using base plotting and putting in a legend, and then I export to PDF, which I know you're going to get to eventually, the legend itself is like the wrong size. It doesn't get rescaled appropriately, like whereas the rest of the plot.
Huh.
So I'm wondering,
Yeah, I guess my first thought would be to use that CEX argument. I mean, so I guess I think of using the PDF function, that sort of thing. That is the permanent record of your plot. So that is what it looks like. So design your plots in the internal thing
to look how you want it
in the PDF. Yeah, that's sort of how I do it. Yeah.
I have a quick question.
Yeah.
Farther up, there
Sure.
was a line that said add numeric to change the species to
Right here.
number classification as opposed to factor. Yeah.
Yeah.
Did you run that? Did that
It's a good
change it?
question.
Because I ran it.
Yeah.
And I realized it was different.
So that doesn't actually change it. So that forces it coerces it to the numeric, right? But it doesn't store that anywhere. So that was when I ran that line. Essentially, it's coming up here on the console, but it's not, changing any of the features. So that was just designed to sort of show you, oh, here's another way that R sees that particular column. Yeah. So you don't actually need to run that line in order to get the next bit to work using the using the brackets.
And so, I mean, I understand what happened with that line right below it, plot.colors, the index.
This guy here.
Yeah.
Yeah.
And so essentially what's happening is when you feed it iris $species, it is that, right? It's like a vector.
Exactly.
And you're asking it 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2.
Right.
And so on and so forth.
Yeah, exactly. So yeah, your R's, when you're using this bracket notation, R is essentially treating this this factor as the index values of which
Gotcha.
level it's on.
Okay.
Yeah.
Okay.
Could you do that without changing it to a numeric, or like could it be a factor?
Well, he didn't change it.
Yeah. So right, and that was sort of the question before. Was this doesn't actually change it? This is just I could, if I wanted to actually change it, I would say iris $species is assigned to be as numeric, and then it'll force it to be a numeric. Here I'm just sort of printing it out on the console.
Oh, okay. So you didn't actually change it. You just
Yeah.
But inside the index, and it's essentially treating Setosa as 1, right?
Exactly.
And so it's have 50 records of Setosa, and so it draws the first element of the plot.colors.
so in that color vector thing, it's working with it's working with them as factors still.
Yes.
Yeah.
Right. Yeah. And so the R sees factors in two sort of ways, both as the name within the element, the character name, but then also which, like the index number of the level
Okay.
that's there, right? Okay, so let's add some lines onto this plot. So what do we have so far?
And sorry.
Oh yeah, go ahead.
That
Of course.
So that method that you showed would actually be really useful because, it doesn't have to be in order, right? Because if it's Setosa, Virginica, it's going to go 1, 3, 3.
Exactly.
And then, so that vector will be exactly matched up with your.
Right. Exactly. Yeah. This particular case was, that's why it was easy just to use the repeat function also, right? This happens to be 50 in a row of each
But
different
this
kind.
is way more general and would.
Exactly.
Gotcha.
Yeah.
But it would depend on which ones come in. Like it wouldn't necessarily give Virginica a 3. If Virginica came second, wouldn't Virginica be the number 2?
Oh, it would be. Yeah. Sorry.
So except that in a factor, R sees the different levels of the factor always in the same order by alphabetical order, I think, right? So when you call, for instance, the levels function on a factor, it's going to return the character vector representing the alphabetically ordered.
So it wouldn't actually matter then.
Right. Yeah.
It would literally just be alphabetical.
Exactly.
So basically, your plot.colors vector would be the color of the level in alphabetical order. Right?
Exactly. Yeah. And so if you wanted to start, this is
if you didn't change it to numeric, right? Otherwise,
Yeah,
Well,
he
so
changed it.
right, but so
Yeah.
yeah, right, and so we never actually did change it to numeric,
okay.
right? So I could have deleted that line totally,
Okay.
and that was just sort of for illustrative purposes, I guess. Of this is what R sees also. But you're right in that those particular index values are inherently associated with the values, with the levels of the factor.
The order of the factor is by default alphabetical when it's created. Like if you just sort of create a factor or something else creates a factor, but it can be changed arbitrarily in the sense that like a factor you can set up a factor in whatever order you want. And like often one of the problems people have with plotting or with ggplot is you need to reorder the factors to get the things in the order you want them to appear, because things will do things by default in the order of the factors, and sometimes you want a different order. So
Interesting.
when a factor is created, it'll be, if you create it from character information, from text information, it'll be alphabetical. But then you could also say, create a factor, use this order of the categories. So in this case, it's alphabetical. When it's set up, it'll default be alphabetical. It doesn't have to be alphabetical.
Cool. Good to know. Any other questions about that? I mean, we can sort of explore it a little bit further too, if y'all want. But yeah, basically, I would call the levels of iris species. Now I know that's the order that R sees those levels in, and then I'll create my plotting colors vector from that. That is one way that you could do it, just to be sure that everything's matching up how you want it to be. But yeah, but you're exactly right that if the order is different, in the actual vector, in the character vector, then R will know, right? It could go 1, 2. Yeah. Okay, so adding a best fit line to a plot. So there's a bunch of different statistical methods that you'll end up using to sort of fit a particular model to data. But in general, we want to think about this particular recipe for fitting that best fit line. So you're going to estimate the parameters of that best fit line using whatever statistical method that you choose. You're going to make up your own X values, and you want them to span the width of the data that you're trying to put that best fit line on top of. So you're fabricating those X values, and you usually want them to be evenly spaced and pretty densely spaced too, so that you can get a nice smooth line when you end up plotting it. The third step is you want to get your Y values by applying whatever mathematical function you use in your estimates from your statistics. And then so you're generating Y values based on your fabricated X values. And then you just plot those fabricated X values with those generated Y values onto the plot. So, in your head, think about those sort of 4 steps, regardless of what statistical method you end up using. That's, if you sort of ground yourself with those particular steps, that'll be good. So I'm just going to use a linear model as a simple example here. And so I'm setting up this model, predicting sepal length based on petal length, and I'm passing it again this iris data frame. And so this is maybe a screen that you all have seen before, just the result from that linear model call. And these are the important bits. So we've estimated, these are our estimates of the slope and of the intercept. And so that's step 1, right? So we've got the estimates from our statistical model. And now we're gonna make up our own X values. Here I use the range function of the petal length of our original predictor to see that, well, that spans from 1 to 6.9. So my fabricated X values, I'm just gonna make a sequence from 1 to 7 and in increments of 0.1. So I'm gonna keep them pretty closely spaced too, so that I end up with a nice smooth. This is gonna be a linear fit anyway, so you could have just done 2 points and that would have been fine too, right? But so in general, you wanna try to keep those more closely spaced. So looking at that vector, we have our X vals from 1 to 7 in increments of 0.1. And importantly here, and this will become clear later, put them into a data frame that's named, right? So this data frame, I'm creating a data frame here called DF, and I'm naming it the pedal.length column, which is one that I'm creating, is going to be equal to those X values that I fabricated. And so to look at that new object that I just created, now I have all of my X values in this single column, 1 to 7, evenly spaced, and then the name of that column is pedal.length, and that'll make it easier to take advantage of the predict function in a second. So the predict function is really nice, and there's a lot of statistical packages that end up using it, coming up with their own methods for it. So here's basically how it works. You use the predict function to pass in your model, and then this new data argument, this is why it needed to be your fabricated X values needed to be in a named data frame, because that's the data frame that you pass into, or that's the object that you pass into this new data equals argument. And in this case, I'm gonna use this interval equals confidence. For linear models, this works really well. For other models, it may not, and probably won't. But so running this line, and then here I'm just gonna force that. So that predict function returned a matrix, and we just want to force it to be a data frame to keep how we're calling the columns of these objects consistent for the rest of the plot, or for the rest of the script here. So I'm going to force it to be a data frame using this as.data.frame, and notice that I use this object name and then on both sides of that assignment, right? So I'm sort of redefining that object by doing that. And so let's look at the objects that we just created. So the dimensions of DF, these were our fabricated X values. We have 61 of them in a single column, and here are the first 6. And the dimensions of our CI object, standing for confidence interval. So again, we have 61 records, 1 for each of those fabricated X values, and now 3 columns. So let's look at what those columns are. So the fit column is the best fit mean, right? So this is going to be our Y values for that best fit line. The LWR is the lower 95% confidence interval for the mean of that best fit line. And then the upper column is going to be the upper 95% confidence interval for the mean of that particular best fit line.
Do you know, this isn't the topic of your talk, so it's not really a fair question, but do you know if predict uses the implied distribution of the estimates, or if it just uses the precise estimate? Each time?
It looks like it
yeah.
doesn't. I mean, just based on how small it is,
Yeah.
I would imagine that it's like the maximum likelihood estimate, or the
point estimate.
I would
and then
assume
the error on the mean.
Yeah, that's the error on the mean.
Yeah, the mean of the estimate of the prediction, but not the error on the estimate of the birth.
Standard estimates that would vary a lot.
It's okay. This is not the topic of the talk. I'll look into it.
Yeah, I don't know.
Okay.
I don't know. Yeah, we'll see the a prediction interval later too, which is maybe gets at your question, but probably not. I think you're asking something different. So yeah, I don't know. Okay, so let's plot the actual data, and I've just copied this code from above. So we've got our plot colors and then our color.vector using that that trick with the factors. And I'm gonna add in our character expander so we can see things. Here are our data plotted and our best fit line. So here's another one of those functions that adds another feature to an existing plot. So the lines function, again, just takes in an X vector and a Y vector. And in this case too, I've passed it a line width argument, LWD equals, just to make it a little bit larger. And that was so that I can see it on my screen. So we may have to make that even bigger. But so the idea here is that X, these are our fabricated pedal lengths. Y is going to be the fit column in that CI object. So these are the expected Y values. And so that just puts our line right there on the plot. So yeah, that's sort of step 4 in that general recipe. We can plot the confidence intervals too using the same idea.
I just have a quick
Yeah,
question.
go for it.
What's the difference between that and an ab line? What's an ab line?
Ab line is another one of those functions that adds a feature to an existing plot.
Right.
So ab line can take just the model as an argument, and then I think it also plots the best fit line. At least with the linear model, it does, I think, right?
Yeah.
Where you just do ab line of model 1, for instance, and I think that would
I was just
apply
wondering
that
if there's
too.
any benefit to lines versus ab lines. If I did this, I would use ab line, but I have no reason for that beyond.
Right. I think if you're just putting a best fit line, that probably makes the most sense, because we're doing the confidence intervals also, and that was the same sort of way of using the lines function. Unless there's a way to do it with ab line also the confidence intervals, but I don't know that. So yeah.
So ab line is not always 1-to-1. I thought it was a 1-to-1 line. Or is it the best fit line?
No, I've been able to just use it as like a.
You can do, because if you call just AB line
It's the same.
and then model 1, I don't know if it works in more complicated models, but it looks like the same.
So right. So starting again here, just calling that original plot with just the data, and then this line here, AB line model 1, puts it on there.
Yeah.
So yeah.
AB line, it's AB because it's like the model is an AX plus B linear model. So those are the two terms. So it'll provide a line that it'll span the whole plot, so you don't have to define the X values, and it just works for a linear model pretty much. So you can give it the model, or you can just give it the slope and the intercept, A and B, and that's what it'll plot. So you don't need to set anything else up to do it.
So you could literally feed it like the coefficients from the model too,
Mhm.
Yeah.
and it would plot the same thing. Yeah.
I know I can do that. We've never used it for horizontal.
That's what I tend to do too. It's easy to just draw horizontal or vertical lines using AB line also, which is what I end up doing with it mostly. So here's our best fit line. And so again, with the confidence intervals, now we're just going to use the exact same X values from our fabricated X values. And now we're just going to use that lower vector in that CI data frame. So these are the lower bounds of that 95% confidence interval. The LWD is equals argument we've seen before. It's just the width of that line. This LTY argument is new. That's the line type. So I changed it to dashed. There's 6 different line types that you can use. The default is solid or 1. So you can use just the number 1 through 6, or you can name it also. There's dotted and dashed, and there's a few other ones too. So running that line. Oops. So yeah, so running that lower line, we put the lower confidence interval on, and running the next line down, which uses the Y values from the upper 95% confidence interval, puts that top line up. Similarly, we can do a prediction or a forecast interval, and this again works really nicely for just linear models generated from LM, but maybe not so much for other statistical other objects coming from statistical packages and that sort of thing. So yeah, you'll have to see if this works, but the idea is similar. So now I'm creating this new object forecast, passing in the model, passing in new data as that named data frame, just like before, and then this interval equals argument, I just make it prediction instead of confidence. And then again, I'm going to force it to be a data frame just for our benefit. And we get a similar looking object. So the fit is going to be exactly the same as the fit from when I use interval equals confidence. It's just those best fit Y values for the given X values. But now the lower and the upper represent the sort of forecasts. So where would you expect new observations to be for a given X value, rather than where do you expect the mean to be for a given X value?
What does that mean? I know you explained it. I don't know how you could explain that any clearer. I just don't. exactly fine. I don't even necessarily have a question.
So I think this is more like a confidence interval as you would think about like, well, if you just plot it, it like
Yeah,
contains
yeah,
way
yeah.
more of the data.
Right.
There's
Less sure about
Yeah.
what you're saying.
That's the prediction interval.
Yeah.
To before. So if you were to predict
New data.
if you were to predict new data, you'd expect it to be within that, as opposed to if you predict the average of the new data.
Yeah.
That's why the other was much smaller, because the mean is obviously going to vary less than the actual data.
Okay. Yeah. Okay.
Yeah, so the confidence interval, as we tend to think of them, is about the mean, and that's going to be narrower than the forecast interval, which is much wider.
As if you're predicting observed new values, not just the mean of observed new values.
Right.
Oops. So here's our plot again, and same idea. So lines, x equals our fabricated x values, y. Now I'm using this different object, the forecast, but still that fit column. But we could have put in the CI object there also. They're exactly the same. That mean value, expected mean value. And I'll make these bigger too. But we can see that our forecast lower interval is much lower, and our upper interval is much higher.
Okay, but that line's exactly the same.
Yeah, this best fit line is exactly the same. Yeah, yeah, and you could get that again just by doing AB line also. Any questions so far? No, last bit. Okay, so this next part is about shading the regions of the forecast interval, which is a kind of a cool feature of ggplot. So I guess that's my other bias too, is that I don't know ggplot very well. I'm learning that also. So yeah, bear with me on my comparisons to ggplot. They might be off base. But so here I am just copying this code from before. And I'm gonna just plot our best fit line in the middle. And actually I'll make that a little bit bigger. Okay, but so here's the new idea. So when we want to make a shaded region, we're gonna use the polygon function. And essentially what it does is you give it a starting point, x, y, and you have it go through each of those x, y values that you give it. And then it'll get to the end up here at the far right-hand side of the plot. And then you give it the x and y values going backwards to the other side, and then it will complete the polygon, and it draws a nice polygon around your fitted line. So here's the code to do that. So here I'm just defining the x values for that polygon, and again I'm using the lowercase c concatenate function. So I am concatenating the fabricated x values 1 to 7, and then the reverse, this rev function of those concatenated x values. Right, so 1 to 7, and then 7 back down to 1. So putting those together, we get our x values. So again, this is going to start way down here, go up to 7, and then come all the way back down to 1. And then for the y values, we're going to do something similar, but this time we're going to go forward with the lower forecast interval. So these y values down here, and then go up to the y values at the right of the graph. And then the reverse, but this time of the upper interval. So it goes on the bottom of the plot, goes up to the top of the plot above, and then comes backwards from there. So looking at the object that we create there.
Where did you get 1 to 7 from again?
So 1 to 7 was our fabricated x values. So when you're trying to plot your best fit line, you sort of make up your own x values and then figure out what the expected y values would be.
And you did the range of the actual data.
Yeah, exactly. And so that was that's it. Okay, line 170-ish. So yeah, the range of the iris petal length gave us about 1 to 7, and so then I created the x values from there. Good question. So by default, R just makes a not filled in polygon around the x and y values that we pass to it. But we can change the color and give it a fill color. but that obscures the data too, right? So we may want to turn down the transparency. And I found this function recently, but it's super helpful. The adjust color function sort of turns the knobs on the red, green, and blue and alpha values in a particular color, so we can turn down the opacity of a particular color using this function. So let's plot the original data again. Clear what we have. Here's our best fit line, which we've done before. This time when I pass a color in, I use the adjust color function. I pass a color argument in, so I'm just going to take black and then use the alpha.f equals argument to turn down the transparent or turn down the opacity to 40%. So it's a scale from 0 to 1. And actually, if we run that particular line, you can see it returns the hex code for that. So it's black, but then it turns down the last 2 digits or the opacity of that particular color. And then here I turn the border of the polygon off also. So now we've got a shaded region around our plot. And then we just added our legend back in here. Like that. So this next bit, oh yeah, go for it.
If we wanted to like plot the lines, or sorry, the points on top of the polygon, we would just need to like plot a blank plot and then add the plot points in at the end or something.
Yeah, I guess that's what I would do. Let's see if it works. I'm gonna set it up. So something like that, and then I'm going to change this to points. Yeah. Cool. Any other questions about the shading? Yeah, thanks for coming.
If it only has one, I guess I'm just imagining a situation where maybe you have like different categories and maybe predictions, and you want to plot, it'd be more like a box for each column.
Okay.
Well, can you do that easily with the polygon, or would it even? I'm just trying to think of what even the X range would be like.
Right.
If you just give it like one value, is it just going to be like a line basically, or could you kind of scale? Never mind.
I guess, are you to make sure I'm understanding you? So do you mean like maybe have a different interval for the different sections or something like that?
Or if you just had like the three groups, and you had just a vertical spread of points, and you wanted to like draw a box around them, you know, like a 95% confidence interval.
Oh, but as a sort of shaded.
Yeah, it's almost more like a histogram, but this one's never mind. I don't.
Okay.
I can figure it out.
All right. Okay, so the next part is about bar plots, and we just have a few minutes left, so we'll get through that and see where we're at. So this time I am fitting another linear model to predict sepal length by species, and this is essentially just how I'm getting my heights for the different bars. So predicting sepal length by species, and now I'm again using this predict function, passing in the model that I just gave it, and now new data equals that argument is again going to be this named data frame where species is going to be Setosa, versicolor, and virginica. So those are the sort of new data that I'm passing into this predict function, and I'm going to get the expected Y values given those different species. And I'm assigning it to this bar heights variable. So these are the bar heights, the mean bar heights, the mean sepal length for each of those different species. And the basic bar plot function is just passing in a vector of those bar heights.
So just to be clear, like you're using predict as a convenience to average by group. right?
Yes.
Those are just the mean values.
Yeah, and in this case, they happen to be the mean. And the reason that I'm doing it is because I'm going to also extract the standard error from that linear fit, and then make error bars on the bar plot. So since I was going to do that anyway, this is just how I was getting the means for it. Okay, so adding some extra elements here. So now the bar plot function, we're giving in the bar heights. We pass in this names.arg argument, and I'm giving it the first initial of the genus and then the species name. And these are the values that are going to appear below each of those bars. This last equals 1 argument, again, just sort of rotates these tick mark labels on the y-axis to be in the reading direction. The color, I'm adjusting the color of our plot colors vector, violet, purple, and blue, all at once down to 50% opacity. And then giving it a main title and a Y label. So I find that with bar plots, the colors can be kind of jarring when it fills in that whole space with a single color. So the adjust color is kind of nice for that.
Does the bar plot by default not have a line under the x-axis, or did that disappear when you gave it the names argument?
That's a good question. I'm not sure. Let's see. So like this should, or you're asking if that I guess that doesn't have it. So yeah, it doesn't. But yeah, I bet you could use the axis function to draw it back in, I bet, with side equals 1. Yeah. And so here's where it was convenient to set up that model for getting those average bar heights. So here I'm assigning a new object D to just the summary of the model so that I can extract the standard error using this particular line here, this the coefficient of D, and then pulling out the standard error elements.
But that's a weird. What do those error bars mean?
They are the error bars on the estimate of the mean by species. Oh no, yeah, right. Because the estimate is the mean height, right?
Why are you multiplying that by 5?
This is arbitrary so that you can see it. 5 is pretty big, right? If you're trying to do a 95% confidence interval or something like that, it would be different. So that's arbitrarily large so that you can actually see. Yeah, right.
I mean, probably you want to use like this, yeah, the standard deviation. If you're plotting the mean, you probably want to use the standard deviation of the distribution or something.
Sure. Yeah.
Which that might be connected to. I'm not sure off the top of my head.
Yeah, I guess I'd have to think about how it would calculate that.
Sorry. No.
Yeah. Yeah. Right. So yeah, this is definitely like a modeled fit, not a summary statistic or not a summary of the.
Which might be I mean,
Sure.
sure, it's just the mean of the group, but if it were a more complicated model, that might be.
Right. Yeah. Exactly. So yeah, good point though. 5 is super large, probably for any purposes, but the bars are pretty small. So that was just for that. So here I just make the lower object those bar heights minus that confidence interval that I just created, and the upper bar heights the addition of that confidence interval to the bar heights. And then to add those error bars, the key is to make this bar plot, but then assign it to an object. So this bar plot is set up pretty similarly as it was before. So bar heights, the names argument is the same, last equals 1. This time I use this y lim equals argument to specify the y limits of the axis, because those bar heights are, the error bars are going to go up above, outside of the axis. I want to give myself some extra room on the y-axis there. So y lim equals, and you pass it a 2-element numeric vector, so I just wanted to go from 0 to 7.5 instead of 0 to 6.5 or wherever it goes right now. Again, I'm adjusting the color, but importantly, I'm assigning it to a variable b. So when I run this particular variable and look at it, b now represents the midpoints for each of those bars. So this is 0.7 right there, the x value. This is 1.9, and then this is 3.1 right there in the middle of that third bar. So we can use that to add those error bars in, because that's where we're going to want them to be, right in the middle of the bar. And we use the arrows function to do that. So arrows will draw, this is another function that adds a feature to an existing plot. And you give it a starting x value, a finishing x value, a starting y value, and a finishing y value. And then there's some other modifications too. Instead of having an arrow, we flatten out the angle so that it's 90 degrees and perpendicular. The arrowhead is sort of perpendicular to the arrow shaft. And then the code equals 3 puts an arrowhead on each side of that bar. And we'll make it bigger so you can see it too. Just like that. And then the idea is similar for adding error bars to line plots or scatter plots or anything like that. It's, you know, use that arrows function, give it a starting x value, a finishing x value, which are going to be the same if you just want vertical error bars. A starting y value is going to be like below the points, and the finishing can be above those points, or either way around. Okay, so that's 11. So thanks for coming out. But yeah, I'm still here for the next hour or two if you've got questions about later on in the code or specific questions about plotting in Bezier.
That's one half of what you wrote, right?
What's that?
It's about half of the script that you.
Yeah, approximately. So there's some more stuff down in there, and yeah, some other methods and tricks that I find myself using a lot. So
It's really nice that it's annotated.
Yeah, it's awesome.
yeah, my pleasure.
Yeah.
I'm excited about the inner and outer margin stuff. That's always awful.
Yeah, yeah.